we know that in the previous lecture we are in a hydrocarbon chapter. So and in the previous lecture we have discussed about, this is Soumen from Hydrocarbons. So in the previous lecture we have discussed about the anti-Markovnikov and Markovnikov rule. The way we start from the, let's say we have an alkene and then you we want to do the addition of the HBr addition to this alkene moiety. And this effect there are two rules. So one is the Markovnikov rule, another one is the anti-Markovnikov rule. So what is Markovnikov rule? So Markovnikov rule is the negative addendum will go to that carbon which leads to the high stability or more stable carbocation generation. But in case of anti-Markovnikov rule, this is something called the peroxide effect, or this is the Paras effect. So in the presence of peroxide, this mechanism is something different compared to the Markovnikov. In the Markovnikov rule, there is the mechanism, the intermediate is going through a carbocation stability, and but here in case of anti-Markovnikov rule, this reaction mechanism is going through a radical way. So what are the things? So in general, so in Markovnikov product, what we'll get? In Markovnikov product, we'll get if we start from the 1 propene, then we can end up in getting the 2 bromopropane. Sorry. And in anti-Markovnikov rule, so there are no possibility to get the 1 bromopropane. So is there any possibility? Is there any rule or any synthetic procedure is available to make this kind of the minor product? In a we know that the always in a major amount of product is the Markovnikov rule is the 2 bromopropane. Okay, so but the minor product is the 1 bromopropane or less, or maybe it is a very trace amount. So if anyone wants to get this 1 bromopropane, is there any methodology available? So then the anti-Markovnikov rule comes to the picture. So in anti-Markovnikov rule, in the presence of hydrogen peroxide or any peroxide, that is benzoyl peroxide, that is C6H5CO2O2. So this is a benzoyl peroxide. In the presence of the benzoyl peroxide, it will go via a radical way. So this is actually one of the radical initiator. So in the presence of this radical initiator, it will influence your reaction and it will forward your product. It will forward your reaction and you will end up getting your expected product. Now in this lecture, we will discuss about the mechanism. As I already told you, the previous lecture I have promised that in this lecture we are going to discuss about the mechanism of the anti-Markovnikov rule. So they are saying the peroxide effect proceed via a free radical chain mechanism. So how this reaction is going? So first we will start from the, as it is saying that it is going via a peroxide effect. So what is the peroxide is available? So one is the peroxide is the benzoyl peroxide. One is called is the benzoyl peroxide. Benzoyl peroxide. benzoyl peroxide. Benzoyl peroxide. Okay. Benzoyl peroxide is what? Benzoyl peroxide is C6H5, C6H5, then CO2, CO, then C double bond O, then C6H5, then C6H5. So this is called benzoyl peroxide. What are the other possibilities there? Other peroxide, that is called hydrogen peroxide, that is H2O2. So in the presence of H2O2 or benzoyl peroxide, it will liberate it will initiate your reaction medium. So this is the radical way. So let's say we start from the benzoyl peroxide. So in the presence of homolysis, we know that the radical pathway always go through a homolysis pathway. Right? Homolysis means there will be one bond breaking will be happen. Then this bond, 2 electrons will share by each other to other substrate, to other reactant. So then homolysis, if it is happens, so then this bond will break. 1 electron will go to the oxygen, another oxygen will go comes to here. Now this bond is break. Now how many benzoyl peroxide will form? 2 C6H5, then CO2 dot. CO2 dot. So total this kind of hydrogen peroxide is generating. So one radical is there. Now as you know that we have always this kind of radical, it's not that much stable. So it has always tendency to break this bond and it will generate one benzyl radical, benzoyl radical and carbon dioxide. Because we know that in the reaction medium, if you have any chance to get the carbon dioxide get out, then there is always possibility it will go out from the reactant or whatever reactant you are using. So then what you are generating 2C6H5 2C6H5 dot plus 2 carbon dioxide. Okay. Now this carbon dioxide, as it is a gas, now it is going by in this way. Now this radical, actually in the presence of HBr, what will happen? So we know that the so then the C6H5 in the presence of HBr, as we are doing the HBr addition, and we have the propene. Propene is the CH3, then CH, then double one CH2. Now we are adding HBr to this alkene moiety. HBr plus peroxide. Then what it will generate? So now C6H5 dot plus HBr. So what it will form? So in the presence of HBr, so this hydrogen will abstract by C6H5. Then what it will form? So this 2C6H6, because one of the hydrogen will abstract by one of the hydrogen radical will abstract by this C6H5 dot. Now let's say not two, only one is reacting. Then what you are generating Br dot radical. Now this Br dot radical has a chance. So suppose you have this thing, you have this alkene moiety. Now Br, where the possibilities, two possibilities there. So where the bromine can go and attack there. Now you have this alkene, you have a plus Br dot. Now there are two possibilities. Okay. Now let me erase this part first. Okay. Now you have a what are the things you have? You have CH3, because we are starting from the propene. CH3, CH, double one, and then CH2. CH2. Now you have this Br radical dot. Br dot radical. Now this Br dot radical with this, what it will generate? There are two possibilities. So one step will go, so that it will be very easy to understand for you also. So this Br dot can either go here or can go here. So if it is go by A pathway, so there are two possibilities, A pathway and B pathway. So A pathway, let's say Br will go here. Then what will generate? CH, then CH2, then Br. Now it is a radical. Now this Br can go here also. Okay. So CH3, CH2, so CH, Br can go, Br can add this carbon also, middle carbon also, then CH2 dot. So there are two possibilities. Two radical is generating. So this is a secondary radical, right? Secondary radical. This is a secondary radical. And this is a primary radical. Primary radical. One is secondary radical, another one is primary radical. Now the secondary radical, what it will form? So in the presence of HBr, again HBr, so then hydrogen will abstract by this proton, this carbon. Then what we are generating? CH3, CH2, CH2, Br. And here CH3, CH, Br, then CH3. So this is a 1 bromopropane we are getting. So this is our actually expected product. Why? Because in the Markovnikov rule, we are getting already 2 bromopropane, but we want to get the 1 bromopropane. And this is the 2 bromopropane. This is the less stable. This is actually less stable because this is less stable. So this don't have any tendency to form this kind of radical. But this radical is secondary radical. It is already more stable radical. So it has a tendency to form always this kind of radical here. Now the question comes, so if they will ask you, so from if you start from one propene, so then you want to get the major product as a 1 bromopropane or 2 bromopropane. So what are the methodology you will use, or what are the method you will use? So in the presence of, if you use the hydrogen peroxide or benzoyl peroxide, you can end up in getting the 1 bromopropane, or if you use the Markovnikov rule, it will go via carbocation stability. So then you will end up in getting the 2 bromopropane, because it is always go via the first bromine will go first, it will go high, H plus will go there, then it will generate one carbocation, so that then the Br minus will comes and then attack to the this middle carbon. There is a secondary carbocation. So one is the Markovnikov, another one is the anti-Markovnikov. Okay, so Markovnikov product is the uh, Markovnikov product is the 2 bromopropane, and anti-Markovnikov product is the 1 bromopropane. This is clear, right? Then we'll go to the homolysis. As they are also showing, the homolysis will happen. Then Br dot, again Br dot, we need Br dot, right? Without Br dot, this reaction will not go via catalytic way. So suppose Br dot is the main radical initiator. Now this Br dot, it will not form, then this hydrogen abstraction will not happen, or Br dot will not go to add to the alkene moiety, which leads to the more stable radical, carbon radical. So that's why Br dot regeneration is also mandatory. So for that, in the end of this cycle, or end of this process, Br dot again it will regenerate. Okay. So now the anti-Markovnikov rule is also done. Now we'll come to the addition of sulfuric acid to a alkene moiety. So suppose you have a CH3, CH, double bond, CH2. Now you have a sulfuric acid. Sulfuric acid. So sulfuric acid is what? H2SO4. Now this H2SO4, what it will generate? So CH3, CH, then CH2, then plus H plus HSO4 minus. Okay. Now we will go to the example. So concentrated H2SO4 adds to alkene in accordance to the Markovnikov rule to form the alkyl hydrogen sulfide by the electrophilic addition. As you know that it will follow the Markovnikov rule, because it is going via carbocation intermediate. Now if it is going via carbocation intermediate, first it will form what? So you have this CH3, CH double bond, CH2. Now let's say you add the H plus. First the H plus addition will happen, then it will form the more stable carbocation. So let's see what are the possibilities actual there. So let's say CH3, then CH, then CH3. This is a plus, two possibilities there. You know that CH3, CH2, then it is a CH2. So two possibilities there. Okay. Now this is a secondary carbocation, and this is a primary carbocation. Secondary carbocation and primary carbocation. But secondary carbocation is more stable compared to the primary carbocation. Now this secondary carbocation, you have these two possibilities there. Now if you have the HSO4 minus, now what will be the product possibility? So one will be, so let me erase this one so that we can get some space, so that we can also write. Okay. So now you have this kind of situation. You have now two possibility. One is the CH3, then CH, then here another possibility is the CH3. So now HSO4, and the other possibility is the CH3, CH2, and then HSO4. Okay, so two possibilities there. So actually this is the Markovnikov product. Hydrogen sulfide by the addition of this is the Markovnikov product. This is actually Markovnikov product. Markovnikov product. Okay. Now we'll go to the next reaction. As also here is also they are showing ethyl hydrogen. So, but they are showing as the they have shown in the case of ethylene, but I have using this propene and then H2SO4, then which is the propyl hydrogen sulfate and the okay. So as you know that, so maybe the internet due to the internet connection, I will repeat this part. So then the addition of sulfuric acid is what cold concentrated sulfuric acid adds to the alkenes in accordance with the Markovnikov rule to form the alkyl hydrogen sulfate by the electrophilic addition. So suppose we have this, if we consider this kind of propene, so let's say one propene CH3, then CH, then CH2 double bond CH2. Now you have an addition of sulfuric acid, that is H plus. Nothing else the H plus source, the hydrogen source. Now you are H plus as a hydrogen source, you are adding a H2SO4. That is H plus HSO4 minus. Now we know that the Markovnikov rule will go in this way. Markovnikov, if it is follow the Markovnikov rule states that if you have a alkene moiety and if it follows the Markovnikov rule, then you will end up getting the Markovnikov, it will go via a carbocation, more stable carbocation moiety. So now you have a two chance. So if you starting from this alkene, now you are adding H plus here. So there is a two possibilities. So one possibility is the hydrogen, a proton can go either this carbon or else this carbon. Let's say first it will go to this carbon. We'll show the two possibilities. So if it is go via two carbon H plus here, so then what it will form? So H plus is SO4 minus. So let's say now this will go and H plus will add here. So then you will generate this is a secondary carbocation. Okay, CH plus. Now H plus will go here and add to the middle carbon. Then you will generate the 1 degree carbocation. Now you have another anion nucleophile, that is HSO4 minus. So there are two possibilities. One is the two secondary carbocation, another one is the primary carbocation. Now this HSO4 minus can go and add to the middle carbon, otherwise the primary carbon. So if it is, we know that the secondary carbocation is more stable, so always it has a tendency to go via this intermediate, not via in this intermediate, because this is not stable. So that's why the reaction will go via this intermediate. So then what we will generate? We will generate the HSO4 minus will come, will add to that carbon, middle carbon. Then we are generating CH3, CH3, HSO4. This is the Markovnikov product. So that means the product name is what? Product name is the propyl hydrogen sulfate. Propyl, and you can see, so there is a possibility. Then we are getting propyl hydrogen sulfate, and it is a Markovnikov rule. So I have only shown one example with the propene moiety, one propene. In your textbook also they have shown the ethylene moiety. So there also you can correlate. So there are no such possibility whether this carbon and this carbon, because this is a symmetrical alkene. So there will be no such problem. Wherever you want, you can go and add to that carbon center. This is a symmetrical alkene, but one propene is the unsymmetrical alkene. So in the case of unsymmetrical alkene, if there are any addition, so addition of the sulfuric acid, then that will follow the Markovnikov rule. Okay. So then we'll go to the next topic, that is the addition of water. So we have discussed about the Markovnikov rule of the HBr addition. Then we have discussed about the sulfuric acid addition to the propene, one propene. Then we are actually discussing about the addition of water to the alkene moiety, because alkene is the also inert substrate, not that much, and loosely bound alkene where the water can add to that alkene moiety. So now you have a water molecule is here. So what are the things water can provide you in the reaction mixture? So one is the H plus and the other one is the HO minus. So in the in situ, what it will form? So water will go and split and it will form the H plus OH minus. So now this H plus OH minus, what it will form? So you have an alkene and you have a water molecule. Now, in accordance to if it follow the Markovnikov rule, what we'll get? So in the presence of H plus, so you have a CH3. If you see the mechanism, So CH3, then C double bond CH2, and you have a extra one CH3 to that methyl carbon, that carbon. So now you have a H plus. Now this H plus can go and add to that carbon, which leads to a more stable carbocation. So two possibilities there. We'll discuss two possibility as well. So CH3, so C, and then so let's say first it will go to the terminal carbon. To that carbon H plus will get protonated, and then two carbon here. So then the carbon generated here. So now it is a tertiary 3-degree carbocation. Okay, now other possibility is here. So if hydrogen can go and add this carbon also. So if hydrogen go and this carbon, so then what it will form? So then CH3, CH. So here hydrogen will come. Also here methyl is also present here. Now what it will form? CH2 plus. So this is actually what 1-degree carbocation. This is very less stable. So it will not go in this way. So it will always follow the more stable carbocation. Now you have a OH minus. So let's say you have a OH minus. Now the product, what will be the product formation? The final product formation. Now OH minus can go and add to this carbocation moiety, because OH minus is a nucleophile, and this carbon is electrophile. So nucleophile always has a tendency to go to the electrophile part. Go to the electrophile means the electrophilic center of the carbon. So now this OH minus will go and add to that carbon. So now what you will get? So CH3. Then here will be another CH3. Then one OH. And then it is a CH3 molecule. So now we are getting the Markovnikov product. And this product is called the tertiary alcohol. Tertiary alcohol. Tertiary alcohol. Alcohol, why? Because OH group is present. That's why it is a alcohol, tertiary alcohol. And the tertiary because it is the quaternary carbon center. So that's why. So now the possibility is the addition of water is also done. Addition of H2SO4 done. Now the thing is the oxidation of the, if we think about the oxidation of the alkene moiety, then what are the possibility you can get? What are the product you can get? So they are saying there are two possibility: alkene on reaction with cold dilute aqueous solution of the potassium permanganate, that is Pair reagent. Potassium permanganate is the Pair's reagent. So in the NEET exam, people can ask you what is Pair's reagent. So Pair reagent is the aqueous solution of the potassium permanganate. Produce vicinal glycol, and decolorization of the PMRF solution is used for the test for the unsaturation. Now you have a alkene moiety, let's say ethylene. Let's say if we start from the ethylene, that is the CH2 double bond CH2. So now you have a water molecule plus you have a water molecule, and then you have an oxidizing agent, that is a dilute KMnO4. Dilute KMnO4. I will not go further for the details mechanistic part because it will take more time. So that's why I will go quickly. What are the possibility product you can get from the alkene? If you start from alkene, what are the product you can get? So one alkene is I have taken the ethylene moiety. So if you do this reaction, what you will get? So let me first erase this part. So then what you will get? You have a alkene moiety. Alkene is the ethylene moiety. Now you have a let's say dilute KMnO4. Now this KMnO4 and the alkene, what it will give? It will give the two OH group. Go and add to that carbon. So CH2, then another CH2, and then OH and OH. This is the OH group, and this is also a OH group. So what we are getting? This is a ethylene glycol. This is called ethylene glycol. Ethylene. This is called ethylene glycol. Now you have suppose you have a propene molecule. So if you have a propene molecule, suppose you have a propene molecule, that is a CH3. This is the one I am discussing about the symmetry alkene, and another one is the unsymmetrical alkene. So then any other alkene part will come from this part. You can easily solve this problem. So dilute KMnO4 and dilute KMnO4 and 273 degree Kelvin. So what you will get? You will get the CH3 then CHOH, then CH2OH. So we are generating this diol moiety. So this decoloration of the KMnO4 solution is used as a test for unsaturation. Okay, so this is the product we are getting from the, if we start from the 1-propene. Now the next part is the acidic potassium permanganate or acidic potassium dichromate oxidizes alkenes to ketones or acids, depends upon the nature of the alkenes or experimental condition. So if you start from this condition, so let's say you have this CH3 double bond CH2. Now if you have this CH2, this alkene CH3, and here it is also another CH3. Now you have a KMnO4 in acidic condition. KMnO4 in acidic condition. Point to be noted, when it is a dilute KMnO4 and aqueous KMnO4, when you are using the aqueous KMnO4 solution, in that case oxidation happens to alkene and it will form the diol to alkene moiety. But when you are using the acidic potassium dichromate or potassium permanganate, that time actually the bond will cleave. This alkene moiety bond will cleave and you will generate what it will generate? CH3 and double bond O. Actually we are generating this one and carbon dioxide and water molecule. So this is the product you are getting from this one. So then again another example we will discuss, that is a butene. That is the coming from 2-methyl propene. So this is the one geminal alkene. So now a terminal alkene. This is a terminal alkene. Now if we use any let's say internal alkene, let's say for an example CH3, CH. So above one example is the from the unsymmetrical alkene. Now if you use the symmetrical alkene, so what you will get? So the symmetrical alkene will get the KMnO4 and H plus solution. KMnO4 plus H plus solution. Then we will get the, this bond will get cleaved. Then we will generate the 2 CH3 COOH. This is called ethanoic acid. This is called ethanoic acid. Okay, so this is called ethanoic acid or acetic acid. Ethanoic acid or acetic acid. Okay, now if we use the ozonolysis of alkene moiety. So suppose you have a 1-propene and if you do the ozonolysis of that particular alkene, then what we are getting? So how it will form actually? So let's say if we see the mechanism part. So let's say you have a CH3, then CH, then CH2. Now you have a O3. O3 means oxygen. One is minus, one is plus. So let's say minus will go attack here and plus will come here. So then you are generating actually CH3. So CH3, CH, then CH2, then oxygen, another oxygen is here and another oxygen is here. So now you are generating the propene ozonide. So the same way here also it is written, this is called the propene ozonide. This is called propene ozonide. Now if you use this propene ozonide and zinc plus water, if you use zinc and water molecule, then what you are generating? You will clip this bond. In this way it will generate. So one will be the CH3CHO, okay, CH3CHO, and another one will be the formaldehyde. So what you are generating? So then CH3, you don't need to go for this mechanism for this part in this stage. So maybe in your higher skill, higher study, you will learn this mechanism. And I don't want to go for the mechanism of this part also. Just to remember that once you have this one, it will go via in this way and it will go via in this way. So the cleavage will happen on this way. So what you are getting? So acetaldehyde and formaldehyde. This is called the acetaldehyde, and this is called the formaldehyde. Now you have this propene molecule. Now you have this propene molecule, that is CH3, C double bond CH2, CH3 and CH3, CH3, and this is, let's say, CH3. Now, if you do the ozonolysis of this one, then what is the main ozonide will form? So the same way, O minus, O plus, let's say, this is oxygen and this is O minus. Now this O minus will go and attack to that carbon. Now this carbon will come and attack to here. Now what you are generating, this is a C and this is a CH2 molecule. So then you are generating oxygen atom here, another oxygen atom here, then another oxygen atom is here, and now you have a 2CH3 molecule is here. So this is a 2CH3 molecule. Now if you use the zinc and water molecule, zinc and water molecule, then what you will get? So you will get this bond break and this bond break. So you are actually generating acetone molecules, CH3, C double bond O, CH3 plus formaldehyde. So this is the two product you are getting from the 2-methyl 1-propene. And normal propene, from normal propene you are getting the acetaldehyde and formaldehyde, and from this propene you are getting the acetone plus formaldehyde. Now we discuss the another interesting example, that is called another interesting example is the that is the polymerization. So we have discussed about the ozonide. Ozonolysis is one of the interesting topic. So as we don't have much time, so I'll only discuss the two examples. So then the polymerization. So what is polymerization? So you may be actually familiar with the polyethylene bags. So from the day to morning, when you wake up from the bed, so from the wake up from the bed to the again going to bed. So that time also, all the time, so every time we are using some other polythene bags or polystyrene. This kind of things are generating from the polymer. So polythene bags and polythene sheets. So polythene actually is obtained by the combination of the large number of ethene molecules at high temperature and high pressure, and in the presence of a catalyst. The large molecules thus obtained are called polymers. The reaction is known as the polymerization, and the simple compounds from which polymers are made are called the monomers. So from where actually it is generating, so this is called the monomer. So let's say if we start from the styrene molecule, so then the styrene will be the, so as you know, the polymerization already you are familiar with the polymerization. So the polyethylene bags and polyethylene sheets, the polyethylene is obtained by the combination of large number of ethene molecules at high temperature and high pressure in the presence of a catalyst. So the large molecules thus obtained are called the polymer, and the reaction is known as the polymerization. In the process we are generating the polymers, so that's it called the polymerization. And the simple compound from where we are getting the polymer, it is known as it is called as a monomers. Okay, so the other alkenes also undergo polymerization. Other alkene also go the polymerization. How? So the other alkenes also undergo polymerization in high temperature and high pressure catalyst. So in CH2 double bond CH2, so that is called the that is called the ethylene molecule. So that is actually called the ethylene molecule. So if you start from the ethylene, one of the ethylene molecule is the CH2 double bond CH2. So now if you start the NCH2, a higher number of ethylene molecule, polyethylene molecule, the higher number n equals to, let's say, 1000 or more than 1000, then in the higher temperature, pressure and the catalyst, you are generating the polymer of this compound. So this is called the polythene. Not only that, if you start from the N-propene, this propene molecule in a high temperature and high pressure, also you can end up getting the polypropene. So that is the whole N, because of the, this is also whole N, because N equals to whatever you will start, let's say n equals to, let's say you are starting with the, now this double bond will you convert to the single bond by just joining of the same molecule in a chain system, chain way. So there will be a number of chains. So if you start from the 100,000, so that will be the end of your product. So if you start from the 100 molecules, so your, as you can see, then if you start from the ethylene molecule, ethylene, let's say if your n equals to 100 molecule. So if you start from the 100 molecule, so then the in the higher temperature and high pressure and within in the presence of a catalyst, you will get the polyethylene molecules. So this will be a one of the your polymer. So polythene. So n equals to, so if you start from getting 100 molecules where there will be no such double bond. So if you start from the any alkene moiety, let's say any ethylene molecule or any propene molecule in the presence of high temperature, high pressure, and in the presence of a catalyst, so then you will get the this polypropene. Polypropene, why? Because n equals to, let's say if you start from 1000 or 5000 or 1 lakh, then your chain number will be, number of carbon will be like that only. So that's why it's the whole n. So then in the presence of whole n, so as you are starting from this calling this kind of alkene moiety, this is the ethylene molecule, this is the propene molecule. So then these are all the monomers. So from this monomer we are getting the polymers. So this the process is called the polymerization. Now we'll discuss about the usefulness of the polymers. So polymers, why the polymers are so much important? So polymers are used for the manufacture of the plastic bags, squeeze bottles, and refrigerator dishes, toys, pipes, radio and TV cabinets, etc. And polypropylene is used for the manufacture of milk crates and the plastic buckets and the other molded articles. And also, though these materials have now become common, so excessive use of polyethylene and the polypropylene is a matter of great concern of us. So now we are discussing about the synthesis of alkene, the usefulness of alkenes, and the substitution or functionalization of the alkene moiety, the addition of water, addition of HBr, addition of halogens, addition of like water, addition of like oxidizing agent. What are the way we can functionalize alkenes? So far we have discussed all these things about the alkene and the alkane moiety. Now we'll go through the alkynes. So alkyne also one of the unsaturated hydrocarbon family. So they contain at least one triple bond between two carbon atoms. So the number of hydrogen atom is still less in alkynes compared to the alkene or alkanes. Okay, so there the general formula is the, so that we have to remember, and the CnH2n minus 2. So CnH2n minus 2. So let's say if Cn equals to 1, then C1H2 minus 2, H2 minus 2, that means H0. Okay, so C1 is not possible, so then we have to go to the C2. So without carbon, without hydrogen, it is not all possible. So then we have to go to the C2. So let's say if it is a C2, then hydrogen will be CH2. So then it is called the acetylene moiety. And acetylene moiety is the, how it is looks like acetylene. Acetylene, and acetylene structure will be CH triple bond A. This is called two carbon chain. And if he is talking about the propyne molecule, one propyne, then propyne means CH3 C triple bond CH. So this is called one propyne. Now the first stable member of alkyne series is the ethyne molecule, which is popularly known as the acetylene. As I already told you, and acetylene is used for arc welding purpose in the form of the oxyacetylene form, and obtained by mixing of acetylene with oxygen gas. Now the alkynes are starting materials for a large number of organic compounds. Hence, it is the interesting to study this class of organic compounds. Now I have taken some of the screenshot from your notebook. So that is the structure and IUPAC name. So let's say If you have a 5 carbon chain on only one triple bond is there, so let's say we go for the IUPAC name. So then 1, 2, 3, 4, 5. So now you have a 5 carbon, so that means pent. So it is coming by pen. Now you have to see whether the other functional group is present here. So now the 1 carbon, 1 triple bond is present here. So that's why 1 ion. So pent 1 ion. Now what we have? Now what we have? So we have now the second structure is the CH3 CH2. So let's say 1, 2, 3, 4, 5. So now this is also a 5 carbon chain. Now let's say first we'll write the how many carbon present there. So pent and the 2 carbon triple bond is there. So pent 2 ion. Okay. Now we'll start the third example if you see. So 1, 2, 3, 4. So now you can see the 4 carbon is present here. So now you can see the but. First we'll write the but. Okay. Now but and the number 1 carbon, 1 alkyne group is there. So but 1 ion. And we can see any other carbon, any other functional group is present. Okay, the 3 carbon, 1 methyl group is present there. So then we can write as a 3 methyl but. So now the structure and the IUPAC name is also complete with the help of the IUPAC number. So 3 methyl but 1 ion. So now the value, if it is, because 1 is not possible, when it is n equals to 1, so then there will be hydrogen will be 0. So that is not possible. So then n equals to 2. We have to start from the n equals to 2. So if it is n equals to 2, then your formula will be C2H2. And the structure will be acetylene, CH triple bond CH. That is called the acetylene moiety. And the IUPAC name is the ethyl molecule. So now the 3, if value is the 3, then it is called the C3H4. So C3H4 is the 1 propyne, that is CH3, C triple bond, and then CH. So that is called the methyl acetylene. And all in IUPAC name it is the propyne molecule. Propyne. Okay. Now the 4 carbon. So if you have a C4, C4 means R and H6. H6 means C4H6. So now if you write the structure CH3, now this is CH2, then C triple bond CH. Now you have this structure. Now what will be the 1 butene or but 1 ion? So because in the 1 position, the 1 alkyne group is present. So that's why the carbon is 4. Number of carbon is 4. So but 1 ion. So now then we'll discuss about the C5 C4H6. So this is the terminal one. So the internally it is possible also. So CH3, C triple bond C, and then CH3. So then what will generate? But 2 ion. But 2 ion. Okay, so we are generating the but 2 ion. In the next class, we will discuss all this example because I have taken, because today I don't have much time. So I just take the screenshot. Maybe the next class I will bring all this information about the alkyne moiety and the nomenclature of this one. And then we will discuss about the triple bond. So what are the triple bond? Triple bond means what? So triple bond means you can see so let's say this one. So this carbon is the sp carbon. Now this carbon is actually overlapping with the hydrogen molecule 1s orbital, and this is a sp orbital, and this is also sp orbital. Now this is a head-on overlap, and this is also head-on overlap. So then there are 2 possibilities. So 2 double bond is there, and you can see. So one is this one. So one is the parallelly here it is the bonding is possible, and it is also possible. And the other way parallel overlap is this one. So this is the another parallel overlap. So then there is as you can see the above the plane and of the paper and in the plane of the paper. So 2 pi bond you can see. So that's why it is a 2 pi bond. So in the 2 pi bond, one is the pi bond, one is the sigma bond. So in the triple bond there will be 2 pi bond and 1 sigma bond, because triple bond is present there. And then the preparation of the calcium carbide. So calcium carbide in the industrial scale, ethine is prepared by treating calcium carbide with water. So calcium carbide with water means the calcium carbide is prepared by heating quicklime. Quicklime is the calcium carbonate. It is called the quicklime with coke. In the presence of quicklime can be obtained. Quicklime is the calcium oxide. Quicklime can be obtained by the heating limestone as a limestone, maybe calcium carbonate. So then the calcium carbonate which react with the calcium carbonate first heated with the high temperature, then you will get the calcium oxide. Then the calcium oxide will react with the coke, that is C carbon. Then it will give the calcium carbide. Then the calcium carbide will again react with the water molecule, and finally it will give the calcium hydroxide. That is called the calcium hydroxide. That is also known as the limestone. Okay, so we'll stop here. And the other things, maybe the alkyne moiety, the one example, okay, let me finish this one example, how to synthesize the alkyne moiety. We know how to synthesize the alkane moiety, how to synthesize the alkene moiety. Now we are going to in another direction where how we can synthesize the alkyne moiety from a vicinal dihalides. Vicinal means the terminal one. You have to remember the vicinal means the terminal one. So let's say you have a vicinal one, that is the CH2Br and CH2Br. Now in the presence of KOH and alcohol, what it will form for OH minus, we know that the is a base. So now this base will come in abstract this proton from here, then OH minus will come here, OH minus will comes here, then we'll abstract the proton from here, then it will come here, then the Br minus will comes out. Then what we are generating? We are generating this one. Now you have a NH2, Na plus NH2 minus, then NaBr and NH3. Then what you are generating? This hydrogen will comes out again, and the Br minus will comes out. Then we are generating the HC triple bond Ca. So we are generating the acetylene moiety. This is called acetylene. The first member of the alkyne moiety is the acetylene moiety, that is C2 carbon. Okay, so we'll stop there. Stop here. Maybe the next week. In between there was some interconvenience of the internet because of the weak internet connection. So again, I have repeated whatever the way the internet connection was loose. So if it is needed for that, which slide if it is not not audible properly, then you just let me know. I'll recover this one, or I'll comes to that part later. Okay, thank you.